Hey folks, today we are talking about geometric sequences in series. Last time we talked about arithmetic sequences in series. So the only twist in a geometric, if you remember, arithmetics moved along by plus 5, plus 5, plus 5, plus 5. A geometric would move along by times 5, times 5, times 5, times 5. So let's start off with our definition. A geometric sequence, underline geometric and sequence, that's what we're defining, is a sequence with a common ratio between consecutive terms. So today's notes are going to feel a lot like last time's notes because basically I just did the same examples but for geometric situations. So if you remember, last time, an arithmetic sequence is a sequence with a common difference between consecutive terms. So last time we would grab a term and we would subtract the one before it. Grab a term and subtract. Now, to find a common ratio, we're going to grab any term and divide by the term before it. So if I grab any old term, if I take 12 and then I divide by 3, I get 4. And then I take 48 and I divide by 12 and I get 4. And I get 182 divided by 48. I better double check. 192 divided by 48 is 4. So every time when you divide any term by the term before it, that finds this thing called the common ratio. So is this sequence geometric? Yes. Because the common ratio is 4. So you try the next one. All right, let's see how you did. Hopefully you answered yes. So this one's a little sneakier because you've got sort of you don't get as nice of a number as like we did up above. So if I take negative 12 and I divide by 36, I'm going to frac that back. I get negative 1/3. Or if you want to be fancy, use your fancy fraction thing. 4 divided by negative 12. Oops. I'm going to start over. Negative 12 divided by 36, then frac it back. Or you can go with fancy fraction thing and do 4 divided by negative 12, and it spits back negative 1/3. And then, or you can use parentheses, negative 4/3 divided by 4, and then frac back. And you'll see, yep, every time we got a common ratio of negative 1/3. So yes, the sequence is geometric because there is a common ratio of negative 1/3. So there's another way to say that it is geometric. So just like last time, now we have a sense of what an arithmetic and a geometric sequence, how they kind of behave. Now let's try to write some rules. So here's a sequence. It's geometric, and we're going to try to write the rule for it. Well, you could try guess and check and kind of figure it out that way, or we can go to our cheat sheet and use this thing to help us sort of narrow down the options. So let's start off first. Arithmetic, this is now geometric. So I'm going to circle this. There's my geometric problem. So if I'm doing a problem and I'm looking, this would be my geometrics. These would be my arithmetics. Geometric means multiplication instead of addition. And again, a sequence is a list where a series is a sum of that list of numbers. So our first example, our first theorem, the rule for a geometric sequence, so that's what we're trying to define, is based on what things do we need to know? We need to know the first term, and we need to know the common ratio. I am going to let you leave a little note here on how to find the common ratio. The common ratio is not as easy to find in arithmetic. In arithmetic, you can just look and you can tell how it's moving. It's not quite so easy in the world of geometrics because you might have fractionals, ratios. So to find the ratio, take any term divided by previous term. And then we plug it into this formula, a sub 1 times the quantity of r to the n minus 1. So let's look at our first sequence. So I need to know the first term, and I need to know the ratio. So my first term, a sub 1, ends up being 152. Ratio, okay, so grab any term and divide by the one before it. Negative 19 divided by 38. You could do it as a fraction, or sorry, as a decimal. I like to frac it back, so I get negative 1/2. Now they told us that this was a geometric sequence, so we don't have to double check it. But if you wanted to, you could grab any term and divide by the one before, and it should work out. Now I want to put these, I want to plug in chug. First term times the quantity of r to the n minus 1. So a sub n, first term, times the quantity of r to the n minus 1. And there's our rule. Now, last time I had you do an example after this. Another one, but I'm going to just have you guys do it on your homework. I don't think we need to do another example of, I think we hopefully have got the idea. So let's move on to the next scenario, and that's the one where I just give you two random terms. So this is where we have to figure out how many gaps there are between the two terms. So I'm starting with a sub 4. Now, in a geometric world, how do things move along? They don't move by adding. If you remember the last time, our notes went whatever term you want plus the number of differences. But we're not adding anymore between terms. We're now multiplying between terms. So I'm going to multiply, and I'm multiplying by a bunch of ratios. So a ratio gets raised to some power. So let's start. Let's count up how many gaps there are first. So a sub 4, then to a sub 5, 6, 7, 8, 9, and 10. So there are 6 gaps. That means that there are 6 ratios. But what's r times r times r times r times r? 6 times we would get r to the 6, which then equals a sub 10. So like before, now I can start to plug and chug here. They told me that a sub 4 was 125 times r to the 6 is equal to, they told me that a sub 10 is 125 over 64. To get r by itself, I have to kill off the 125 first. So I would have 125. Actually, I'm going to do this with the frac button. So I want to have a fraction. And because I'm doing this divided by this, let me see if I can do I want to do 125 over 64 divided by 125. So I need another fraction on the top. So I'm going to hit a over n again. 125 over 64 over 125. And that spits back 1 over 64. Now let's say you did it with parentheses. 125 divided by 64 divided by 125. And you get this. Just frac it back. And either way, we get 1 over 64. So my equation now says r to the 6th equals 1 over 64. Who's keeping r from being by himself? To the 6th. So I'm going to 6th root both sides. Now you might have to do plus or minus. Sorry, it's kind of tempting to do plus or minus here, but you don't have to worry about the minus case. In this case, our ratios are always going to be positive. If they were negative, your terms would bounce back and forth between positives and negatives, which would cause quite a pain. So my ratio is 1/2. I'm going to underline that. That's half the story, because in my rule, I need the ratio, but I also need the first term. So now I have to work backwards from a sub 4 to a sub 3. Now, this is how I move forward. I times by 1/2 to move forward, so I would divide by 1/2 to move backwards. Or, and some of you probably already know it, but if I divide by, I need to take 125 and divide by 1/2, and I get 250. Well, that makes sense. Dividing by half is like doubling. So I'm not going to keep doing it on my calculator. A sub 2 then would be 250, gets doubled to be 500. A sub 1 doubles to be 1,000. So we can now take our ratio and our first term and plug it in again according to our cheat sheet. It's a sub 1 times r to the n minus 1. So a sub n is equal to a sub 1 times r to the n minus 1. So just like last time, we did another example of this last time when we did arithmetics. I think I'm going to have you just do your example on the homework when we get to the homework. So we still need to talk about sequences and series. We still need to talk about the series part of this. So these are pretty straightforward. I'm going to go ahead and highlight a couple of things on our sequence sheet. So this is a sum for a geometric series, but so is this. So there's two of them. And we're going to come back to this one in a minute. And this is because this is a infinite geometric series, and it gets kind of tricky on how that works. So we'll come back and talk about that in a second. So the sum of the first term of a geometric series, what are the things that I need to know? I need to know, again, first term. So if this is a sub 1, this is a sub 1. So whatever is in front of this in my formula is going to be the first term in my theorem. And then from there, I can highlight my ratio. Whatever this is ends up being whatever these are. And then last but not least, we want to highlight our number of terms. So that would be the number of terms. This would be the same number of terms. Okay, so let's plug and chug. So keep this handy. I'm going to try to refer back to it too. So in this case, who is in the same spot as a sub 1? A sub 1 is 4. What is r? R is in the same spot as 3/2. So I'm going to put 4 here. I'm going to put 3/2 here, and then how many terms are we going? Looks like we're going 20 terms. So this one's a little bit messier of a formula, but it's still just plug and chug. So my first term is 4 times the fraction. So 4 is my first term times 1 minus. Now my ratio, I'm going to circle that in a different color. So my ratio is 3/2 close it to the power of n. For us, n is 20, so I'm going to put a 20 up here. Over 1 minus r again. R is 3/2. Oh, I didn't even need parentheses around the denominator, darn it. I mean, around the denominator I did. I didn't need it around the 3/2. This is something I can type into my calc. 4 times alpha f1, parentheses, 1 minus, I'm going to go again, alpha f1, 3/2 to the 20th, close it. And then my denominator, 1 minus alpha f1, 3/2 and we get this sort of weird, messy number. It kind of makes sense. If you take 4 and keep timesing it by 1.5, 1.5, 1.5, you're going to get a lot of decimals. So our end answer would be 26,594.05. I decided to go to 2 decimal places. That's usually a pretty good number to go to. How could I change this? Let's pick a different color for next year. About let's make this blue for next year. Okay, so hopefully you got the idea there, plugging and chugging pretty much into that formula sheet. Now we're going to look at this one. So I'm going to start off doing it the same way. Problem is, this goes off to infinity. So it's tempting to think, well, wouldn't anything, an infinite number of things added together just add up to infinity? And that's not the case. But it's not the case only in certain scenarios. So for a sequence, for a series to not always add up to infinity, this has to be true. Your common ratio must be less than 1. This is what we call convergent. This is a convergent series. If the absolute value of r is greater than 1, then we would have a divergent series. So let's take a look. Did I say earlier that r couldn't be negative? That's not true. My r's could be negative. I have to look into that a little bit more, what I said. I'll go back and watch it. So if r is less than 1, if your series, look at this one. What's your r value here? My r value is 2/5. So if I take 4 and I times it by 2/5, I'd get a smaller number. And then I take that number and I times it by 2/5, I would get an even smaller number. And I times by another 2/5 and another 2/5 and another 2/5. Eventually, that value that I'm adding on each time would become 0. That infinite term would eventually disappear. So this is because r is less than 1, I can actually use my formula here on a convergent series. So let's do this again where we circle stuff. Okay, this is my a sub 1. This is my r value. And what's nice about the infinite series, it's just a sub 1 over 1 minus r. You don't have to get real, it's not real complicated. So it would be 4 divided by the quantity of 1 subtract 2/5, which, what would that be? That'd be 3/5, so that would be 20/3. This would end up being 20 over 3. Grab your calc and figure it out if you don't agree with me, but all right, you try the next one. Pause, try the next one on your own. Okay, hopefully some alarm bells went off. You cannot calculate this because my r value is greater than 1. Now, what's weird is you could actually plug this into the formula and get an answer. So my first term would be 4 over 1 minus 5/2. That would be, so 2, that would be negative 3/2. Flip and multiply would be negative 8/3. So you can actually get an answer here, but it's incorrect. It's not the right answer, and that's because you are not allowed to use this formula unless r is less than 1. So if r is greater than 1, you don't have a sum. This would add up to infinity. Or if you wanted to write, you could write no sum either. That'd be fine. No sum. So be careful. I would recommend at this point, pause. I'm going to let you write a little note to yourself. I'm not going to write it for you, but I'm going to give you the opportunity. Have kids write and note to explain how this works. So I'm giving you a chance to add a little bit to your cheat sheet. How do you know when you're going to get an infinite series with an actual sum and one that just goes off to infinity? After that, attack the homework. Good luck.